Do you need to? Standing up on top of a mountain and looking out there, and to both where you came from, but also where there's new places you could go that you have never seen. I believe that feeling is one of the feelings that scientists have often. It turns out that research sometimes feels like a hike in a fog. And it certainly felt many times last year a little bit like that to me. I don't know how you felt about this. Kind of isolated from others, really recognizing that, of course, what we're doing is important and what we're doing is serious. So I feel a little bit like that person on top of the mountain right now. And of course, the reason I'm feeling so hopeful is because the reason many of us are here and we just could have lunch is because we have a vaccine that is the product of decades of research. The power of science has never been more clearly demonstrated than what just happened in the last year. And those of you who are, feel the same way, tell that story, learn about that story and talk about it. I mean, yes, I'm not a biologist, I'm an astrophysicist, but who wouldn't be seeing the power of science there more clearly demonstrated than changing lives and actually saving lives of millions through research that has been done in labs all over the world. So I just really appreciate that. So I want to tell you a little bit about what we're doing in the Science Mission Directorate. And absolutely not clear how this slide knows how to advance. If you were to slide, how would you know? That's right, but okay, good, I got it. Oh, it works now. All right. All right, so basically, the first thing I want to just quickly talk about is why we do science at NASA. And I'm going to start here all the way at the right, then work my way to the left of the slide. We do research at NASA for 3 different reasons. And I'm going to talk about the first 2. They're really similar, but one is a subset of the other, okay? The first one is we discover the secrets of the universe. Whether those secrets are, in fact, in the deep universe, the beginning of the first galaxies that we're going to observe with the James Webb Space Telescope, whether it's dark matter, dark energy, how a galaxy works, planets around other stars. Secrets of the universe tell the story about us. And they tell the story about us being part of that magnificent nature that we're part of. Secrets of the universe, of course, also shape our environment. And so there's not just looking at deep space, we can look at that when we look at, our own biology, about our own Earth, as well as the planets around the solar system. Discovering the secrets of the universe is worth doing, even if there's never a startup that comes from it. I'm going to talk to you about how excited I am about when that occurs. But by itself, it's already important enough, because it does not only shape what we know or decide what we know, but it shapes how we think about ourselves. It's a deep part of who we are. There's one topic that is a fundamental science topic that has been with humanity as long as we wrote conceived texts, and that has to do about where did we come from and is there life elsewhere? Any child that looks at the night sky will ask you that question after a short time. You don't need to prod. That's what happened to me. Yesterday I met with middle schoolers down at the Science Center, and 80% of the questions were those type of questions. Where is there bacteria elsewhere? And so forth. Questions that frankly have changed in nature in the last 20 years in a way that there's almost no other field that has changed dramatically. We have planets, over 4,200 planets that were discovered in our own galaxy outside of the solar system. We have learned about water oceans that have complex chemicals in them in moons around other planets, such as Enceladus, Europa, and other worlds like that. And we've learned about a wet past of Mars that, to our best of belief and knowledge, 3 billion years ago, in fact, could support life during a time where that occurred on Earth. Searching for life elsewhere is about the transition from the physical and chemical world to a biological world, the transition we don't yet understand. And we have n=1 example to examine, which is life on Earth. So whenever you go from n=1 to n=many, is what happened in the theory of stellar systems. And in 1995, when those 2 planets were announced at that conference in Rome, I still remember, I was not at the conference, I was just a grad student. When they were announced that day, first of all, 50% or so of the scientists said, that cannot be because it opposes my theory. And the other 50% started cheering because they realized what happened there. And of course, the theorists that were there defending their theories all were wrong. The world is full of surprises. And when we look at our own solar system, sometimes we don't realize the way I think about it. It's what's bold-faced and what's not. What's actually important about our solar system, what's not. By observing solar systems elsewhere, we're learning about our own solar system and the dynamic nature of that solar system in a way we never appreciated. What's really cool about our research is that research from in and from space is protecting and improving life on Earth and in space is a benefit from that in a way we would have never guessed. When the first fuzzy images were made of the Earth from space, nobody would have believed that their grandchildren, their children are walking around with computers in their pocket that not only have the latest space imagery that high sophisticated spacecraft are taking right now, that those space imagery are saving lives today in places where storms are occurring and people need to take shelter. And also those space images are actually also helping kind of communities, entire communities, deal with a changing environment. Protecting and improving life on Earth and in space also relates to the benefit of the science, in my mind, that comes from the discoveries. If a discovery can lead to a company that can create jobs, let's jump on it. It's incredible to have that benefit as well. It's not the reason we do fundamental research, but it's one of the benefits in many cases that is there. And what we have done now is we've started applied research programs that actually put fuel on the fire that is creating that benefit overall. We look at life not just on Earth, but also in space, because we think that that is a future where that we have a lot more of, and what we're learning from there is, of course, having benefit on Earth as well. That's why we do research for these 3 reasons. All right, there's a bunch of overall, divisions. Talk about Earth science, roughly $2 billion, 2.25 is the new president's proposal. Really focused on the fundamental science of the Earth as a system. The most beautiful planet we've ever seen. We've discovered anywhere. That's what that is there. Heliophysics is really all about the space between the sun and the space between the planets and the effects that come from there through the both space weather perturbations, but also that state of matter that is what 99% of the universe, the universe as we can observe it with atoms and nuclei and so forth is made out of, which is the state of plasma. It's a non-obvious electromagnetic type of tangled mess, frankly, non-linear in many places. Of course, it's the reason why we have a magnetic field on Earth. It's also why we're shielded from space weather, and how much of X-ray astrophysics has its root from that. Planetary science is about bodies around, including the moon, and then all the bodies in the solar system, including, I don't know whether you're on Twitter or whether you're into this kind of stuff, but the Europeans just announced a Venus mission this morning, where, by the way, NASA is spending $300 million on that mission. So I call it the Venus hat trick. 10 days ago, there was no Venus mission that we had done for over 30 years, and now we have 3. So that's the the Venus hat trick, there will be a decade of Venus research in a way that frankly will transform not just how we look at Venus, whether it had harbored life or the potential for life early on, the history of its thick atmosphere, but also how we can learn about that, about our own atmosphere, our own world. Astrophysics, I just met one of your professors who won one of the first highly competitive proposals to get James Webb time. And so astrophysics, of course, is looking at some of the simplest questions that we're answering, of course, with the tools of science. I love it. Biological and physical sciences relates to what we can do in space that is very hard to do here, and of course has benefits. I just talked to you about it earlier. I'm not going to repeat that. And the Joint Agency Satellite Division is the one that helps NOAA, the weather agency, build the spacecraft that creates the weather forecast that I already talked about. So this is what we're doing. So if you look at all the funding up to biological and physical sciences, you just gave the number, it's kind of 7.3 billion right now. Order of magnitude. If you add the Joint Agency Satellite Division, it's another $500 million on top of that. That is appropriated through NOAA. So that's what we're doing. Your goal is not to read all of these, but those are all the missions that are there. Each one of them has a story. Let me tell you one of them. You see this line up there? When I was a grad student, a master's student, and I still worked at the University of Michigan, still worked at the University of Bern. A professor told me, I was looking for a master's project. It's like, oh, I have this project, but it's too hard. We're way behind. And God, I believe in students. I was one of them. That's not primarily why I believe in it, but I've seen what students can do. But here's what happened. I basically said, well, can I at least hear about it? I was a sensor on the WIND spacecraft, which looked at space weather. First high resolution sensor, and of course I took on the project and worked on it, and basically it's still part of my portfolio. It's really, and I know, let me tell you a secret that may not be that secret, certainly after I tell you about it. My thumbprint, the glove thumbprint, is on the inside of that sensor, and frankly I got trained to assemble it, because I was like, I want to actually build something, not just design it, actually build it. But I remember when I assembled it, I slipped with my thumb, and I'm like, do I tell anybody? So I actually went and calculated what the impact would be on the UV suppression, which is why that thing needed to be there. I realized it's absolutely negligible, so I never told anybody. So anyway, if you ever go pick it up, you find it. So anyway, so each one of these has stories. They're stories of discoveries, but the reason I'm telling about myself is they're stories of people. They're stories of teams, not individuals. Kind of every mission from NASA is a story of a team that has diversity of opinion, of background, and so forth, coming together and doing something that one of us cannot do, which is to build a system that changes how we think. Those kind of things teams do. And I am a champion for teams. And that's why when I was, yesterday I met one of those teams, Astrobotic. There's two things that relate to Astrobotic that are on the moon there. The first one is the Peregrine mission. The second one is the Griffin mission. Both of them are being done in town right now. That's why I visited the team. When I was here, it's like, I want to come meet you just because I want you to know that I would like you to consider working with us on one of those teams, perhaps together with your professor, doing amazing research like the professors I just met, whether it's new computing technologies in space, whether it's, James Webb work on our planet, kind of new proposals that are being written to look at the Earth in new ways, and everything in between. That's what I hope you do. Also, when you're done, we have a lot of work. The budget we have has never been bigger in the history of NASA and science. This is a field I hope you can see a future. It has been an amazing career for me, even before I went to NASA. So for me, that's what we're doing. I'll tell you three things before I stop and turn over the discussion. The first one is a picture that has made history. So the picture you see is a rover that's hanging from 3 wires. By the way, where does it hang from? It's a rover. It's basically right now, it's over the surface of Mars. This is February 20th. It's over the surface of Mars by about 2 meters, and it's hanging from these straight wires. You see them there, kind of going down there from 11 o'clock to 5 o'clock. That's roughly the direction. And there's one threaded thing. Do you see that? Okay, so on top is a sky crane. It's basically a vehicle that's running on boosters. You can actually tell some of the impact of the booster because you see that how dust is kind of, you see these round, kind of in the left bottom corner, you see these round shapes. That is dust being moved by the boosters that on top, blowing down fuel that is being burned. And it's taking a picture of the rover just before it drops it off. And so that's what happened, of course, as we landed Perseverance on Mars. The best name ever. By the way, he named it 2 weeks before the pandemic started. I picked up a lot of flack for naming it Perseverance because people said it's not inspiring. And I'm like, why is it not inspiring? Of course, I don't know about your story, but I'm the first in my family to graduate from college. So those of us who had kind of difficult situations like that get Perseverance immediately. All of us who have tried hard things get Perseverance immediately. Because that's just like mission is a key ingredient to success. So Perseverance on the way down. We already have amazing science we're taking now. We're actually rolling. Just this morning, I got an update. We're just a couple hundred yards away from where we're going to drill the first samples. We're in a place kind of away from by roughly a mile from a watershed, from kind of a stream that went into a kind of a crater lake that was there, but water has flooded all the way to where we are. Something we didn't expect. We just happened to land there. We're looking around. We're seeing all these flood indications. You immediately know it. If you've been in Nevada, you understand what it is. Just look around. It looks very familiar. You see, these are sedimentary things. There's water that came from there. And that's exactly what it is. That's what we learned from, of course, looking at the geology of it and all the measurements. But that's the picture I wanted to show you. This is hopefully your favorite picture there, Professor, the James Webb Space Telescope. This is actually 3 weeks ago. The James Webb Space Telescope is a telescope was almost too hard for us to build. It took us almost what will be 2 decades. And frankly, there's still a lot of agony until it's in orbit. We're going to launch it later this year on a European rocket. By the way, I did not come up with that idea, but anyway, I'm sure it saved money, $500 million or so, and I wish I could get that money. Can I pay $500 million? Anyway, so we're going to be excited about launching it there. The rocket is very safe. It just makes the discussion a little bit more complicated. But anyway, we're going to launch it, and then in most cases, just like this Mars thing, for most missions, when you launch it, most of the risk is out. It's like, well, we're good, we're out of gravity. Mars is a lot harder to land than to launch. Well, this one, the hard thing is to deploy. Okay, let me give you some numbers. For it to deploy the way it should, there's 303 single point failures. So anything in these 303 that is failing is basically making the whole telescope a total failure, not just partly successful, a total failure. So you say, well, how does that relate to Mars that I just told you? Well, 3 times worse. So this one is 3 times harder. By the way, the investment that we put in here together as an international community is close to $10 billion. Mars, by the way, was $3 billion roughly. So you see 3 times worse roughly also. So I'm going to feel a lot better when this thing is deployed at L2. Am I confident we'll deploy? Absolutely. The team is doing exactly what they should and doing the hard work as a team. I've observed this team, and it was not always a great team. It's really hard to build great teams, but it is behaving exactly like we want them to, and I have full confidence we're going to do that. We're doing everything we can. And just like what I did with Mars, when we shipped it to the Cape, I called up a number of people in every level of the organization, said, tell me, is there anything we could have done better to make this mission successful right now? Are you aware of anything? And the answer was no, we did everything we could have. Well, that's what we're going to do. I'm doing these calls now here because we're so close to getting it into a container and shipping. This is a telescope that is being assembled right now. It's a collaboration between India and the US, and it's a totally transformative new observatory of the Earth. It's called NISAR, the NASA-ISRO Synthetic Aperture Radar. It combines two different radar systems together to provide data that together in a given year doubles the data of all of the Earth science missions. It's bringing data to space, big data to space, in a way that nothing ever has. It's the first of such missions, and frankly, it will be for disaster relief. It will be one of the key elements that will be there, whether it's geologic events or kind of flooding events, things like that. This is one of those missions that not only has questions, science questions that drive it, but application domains that drive it. So the reason I'm telling you all this, we're here in an engineering department. Of course, all kinds of engineers are building this. Really consider us as you look at your careers. This is at JPL. We have centers in various places in Goddard Space Flight Center in the state of Maryland, and as well as others that do these kind of missions. But the other reason I wanted to talk to you about this is because it's really a revolution of data science. Let me explain to you what I mean. The decadal survey that tells us how we should do the next generation space observatories talked about 5 investigations that together should allow us to observe the Earth system. They also said the way we should look at this is really as a system overall and combine the data of these various assets in a way that allows science to make rapid advance, but also for applications, the use of those data to be there. So think of it this way. I just talked to you about NISAR, which falls in that category down there. We just announced the last 2 weeks, the beginning of all the other observatories here, all the other investigations here that together form that observatory. See that circle in the middle? Think of it as a tremendous cloud-based platform where all the data from all of these observatories come together. These investigations will work together as one single observatory of the Earth system and will basically analyze what is there and allow you, the researcher, to learn new things about our Earth, but also you who is actually affected by the change in climate, affected by natural disasters, to take advantage of the data that are there in a direct fashion. Every one of those investigations is not just driven by science objectives, but by application objectives, and the application users are in the room. So in other words, people who know about farming are there, about fisheries are there, disaster relief, they're in the room as we're building this. So we're flipping the paradigm on its head. We're not building a space observatory and figure out what we can learn. We're saying we're doing a data system that is there and learning how we feed it with observations. There's a number of things that Decadal also talked about that we should focus on with new advanced exploration eyes, so to say. Some of these things we actually don't know how to measure really, because they're really important, but we don't know how we do it from space. We need to do it from space globally. Atmospheric winds, I want to tell you about, right? Winds are easy to measure down here if it blows in your head, in your face, but if you go actually higher up, the winds are really what is the biggest kind of changer of forecasts. You know, whether the wind is slightly off and kind of moves storms in one direction or another, decides whether or not you're going to sit at the edge of a hurricane or not. And these kind of measurements we're going to want to fly. So that observatory will also have new innovative tools that go into it. So the reason I'm telling you all this, as you're looking at your career and your opportunities, think about how we can deploy computer science tools, data analysis tools into this space of Earth science in a way that actually allows us to learn and to help people in the same time. Again, the major reason I'm here is because I believe that the only way we can be the best agency is that you, here, the community at Pitt, you with your own careers are either part of this or something like it that really helps and moves us forward with the power of science, research, engineering, and the kind of tools that you're learning in this institution of higher learning. So basically what I'd like to do is stop here and go into a Q&A, into a discussion, and I don't know who's going to lead that. You are.
Dr. Zuckerman was adamant about this being interactive and being able to hear from you all. So we did get some questions at the time of registration, and we'll start out with some of those.
And David, I'll feed you questions
Yeah.
from Zoom, so people can ask their questions via chat as well.
So those of you on Zoom, if you have some questions, you can certainly post those. So I'm going to start with a question. Actually, it's a hybrid question from two postdocs, so we'll combine them. Mickey Chung and Noah Sargent asked about a general understanding on what NASA is looking for in regards to research, developing physical experiments and devices, computational techniques and approaches, new material discoveries. What is needed for future space exploration, or just the mission in general, the mission areas in general?
I really appreciate the question. So I just want to tell you that the first thing I'm going to do is recognize that I'm not the only directorate at NASA. So I just want to start with that. So I have a technology directorate that is very much interested in materials, new approaches, kind of new technology. And in fact, some of the technologies built here at Pitt are flying on platforms that are in part funded by the space tech, by my space tech colleague. So space tech is besides funding university research, they're actually also doing a lot of work in SBIRs and STTRs, which are sometimes partnered with universities, just like where they are, and they're focus areas that change over time. And what you need to do is just really go to space technology, NASA, and you'll get to the link that basically allows you really quickly to look at the priorities that are there. As far as we're concerned in science, we have the priorities are really focused on these science disciplines that I talked to you about, right? So we have technology spaces too. We have technology programs in every one of our disciplines, and they often work with sensor technologies. Some of them are platform technologies. What are novel ways of doing that, including some of these data things I just talked to you about, AI, machine learning. We're funding them. So often, frankly, the way we're doing it is through a research and analysis process in which we want to fund the best proposals. And frankly, we don't want to tell you too much what you should propose, right? The overall direction is really given by a national consensus, which is the National Academies to tell us what that is. So in that sense, it sounds like a cop-out. So we fund a really broad range of technologies, but also more even of sciences, all the way from components to entire systems that are often built by university principal investigators.
Thank you.
Sure. Himanshu Kolkar asks, with more likelihood of Starlink-like projects and hopefully the success of JWST, I guess what's your sort of outlook for more orbiting telescopes and other platforms like that? Is it a growth area or not?
Can you summarize the question in case those on Zoom did not hear that?
So you're asking about the Valley and in the future of orbiting platforms looking at the universe, such as Starlink, being of course an inhibitor of some of this for observers on the ground. So the way I want to talk about this is from the beginning of NASA, there's this female leader called Nancy Grace Roman. She was one of the first PhDs of the University of Colorado, of the University of Chicago, and actually basically joined NASA and was the first female executive at NASA, and she invented space astrophysics. She basically said, look, the atmosphere is only transparent to a small band of electromagnetic radiation. No X-rays are basically coming through, very little UV. And basically on the radio side, there's whole bands, because of the water and molecules that start shaking and wiggling, right? They don't come through. And so there's whole windows that we don't see. We need to go to space to observe that. For that reason, from the beginning, by the way, many people refer to her as the mother of Hubble, because she was really the one, together with some other partners, such as Lyman Spitzer at Princeton and others, that will Hubble into being the most relevant space investigation we've ever done in terms of publication impact. Today, 30 years after the beginning, Hubble still has 800 publications per year. And that's just absolutely incredible. That, by the way, is at an investment of 75 million per year, which is, if you look at the investment per publication cost, it's one of the best investments ever in these kind of things, even now. So as we go forward, space telescopes will remain absolutely relevant and will increase in relevance as we especially look at some of the work that relates to multi-messenger astrophysics, in which we look at, for example, neutron stars that are emerging and have emissions of X-rays that really are the kind of fingerprint of the physics that happens in that event. Physics, of course, that's really important to us. I was pointing to my ring, which is out of platinum. My wife gave it to me. That platinum was made in a neutron star launcher. And we know that with pretty high degree of certainty now because of observations we made that way. The Starlink stuff basically is, on the one hand, you should know, I work with tech companies on ground-based internet elsewhere. I believe that information is power. And I think it's great to develop information and internet to communities without having to build big wires that go across forests and so forth. I think we should be able to do that, but we need to do it responsibly in a way that does not take away the power of ground-based observations. What we observe so often is that technology makes progress faster than regulations do. And this is one of those things. It's just one example. I could come up with 10 examples. Well-meaning people get into trouble because of that. We learn about boundaries of things we should be doing and should not be doing. I just want you to know, I'm actually far less worried about Starlink itself because it's a US company. We know their phone number. We know how to talk to them. The fact that international players in various parts of the world are trying to do the same is what worries me. And we need to create a consensus of how we deal with our dark skies. And the astrophysics observations, especially in the radio realm, that frankly are at this moment in time not addressed in these massive constellations. It will be the end of certain observational methods if we're not careful. So it's just part of innovative progress. And yes, I believe in space telescopes, but we shouldn't do space telescopes because we destroyed the sky over us. We should do space telescopes to supplement the amazing work that we can do in the middle of the night sky from various parts of the Earth.
So graduate student Theodore Schwartz asked whether there's a science mission idea that you're extremely excited about, for which the science is not quite there yet, or the technology is not quite there yet to conduct the mission.
So I'll give you 2 examples. So by the way, every good scientist should have like 10. I call it a cemetery of good ideas. You go back and figure out whether they're still, these ideas are still dead or whether technologies have caught up. Like 2 or 3 things I'd like to do, right? I'll talk about 2. The first one is Enceladus, Europa are both ocean worlds. We know they have 2 or 3 ingredients. They have liquid water. They have a crust that is cracked. We think there's water coming out and spurting into space from both. With Enceladus, we're 100% sure because we flew through one of those. In Europe, we're puzzling over it. We saw observations from Hubble, one of the 800 of that particular year, was a publication of that. What I'd like to do is figure out how we could go swim in that ocean with our robot and really do the analysis of astrobiology that is required to really learn whether or not these underwater kind of geologically heated oceans are a source of complex chemistry or perhaps life. So that's number one. Number two is, as we're looking at these exoplanets, planets, even the closest star to us has planets. One of these planets are actually in near the habitable sun. One of them, people argue about it. I'd like to figure out how we go visit those things. And we're not going to do it in one leap. But you know, the way we do research is on the log axis. So let's go halfway, you know, on the log axis, which of course means 10x off. But do it 10x over Voyager and learn how to do it. That requires propulsion technologies, smart autonomous systems, and so forth. I'd like to do both of these. Neither of them is achievable right now for many reasons.
Any questions from the live audience?
With an ever-increasing mission loads of the planets and reliance on the deep space network, do you have any plans to further invest in that so that there's no new of data from existing or future planetary missions?
I'm just going to summarize again, just assuming that not everybody heard it exactly online. You're asking about the importance of the Deep Space Network, the increasing of portfolio, and whether we're going to invest in the Deep Space Network. But of course, you're referring to the 3 big antennas or clusters of antenna in Madrid and Canberra, Australia, and then in California that are basically the majority of all data that come down from planetary missions, including from L1, the Lagrangian point L1, where all the space weather forecasts are, and then L2, where James Webb's going to be. The answer is we have actually received a report from both the planetary community and also from the IG, which is kind of the government watchdog that told us we need to watch this and really invest in it. We're doing both. So we actually created a kind of governing process in which human exploration and operations where they're sitting, and we come together with a board of users and actually drive investments towards that. The investments are in 3 ways. The first one is deferred maintenance. We have not put enough maintenance in it. So actually we've had more outages, just, you know, like your car, if you don't take it into the shop, after a while, it will start sputtering. So we have that, you know, you need to bring it in and invest some money and then it's going to be fine again. So we're doing that. The second one is to build out some technologies, but some antennas by building new antennas that we can also add together so we can make bigger effective aperture antennas using new technologies. And the third one is by driving towards an optics communication path, which is we're trying actually next year, we're building a deep space optical communications platform that we're going to send from kind of the asteroid belt from Mars sent back to the Earth data. So those are the 3 investments we're making. One of the Venus technology demonstrations of the Venus missions actually is an atomic clock, deep space atomic clocks. Like, what does that have to do with communication? Well, you know how the internet works, right? If we all have exactly the right time, we can actually almost amp up by a factor of 2 the bit rate instead of doing kind of the handshake protocols. We can do kind of, if you want, the one-sided protocols with good time stamps. So that's the other thing we're doing. So we're actively investing in that. The biggest strain on that will be when humans are at the moon. So that is kind of a 4th element that's outside of my domain, but it's really, really critical. The question just really is, we're asking right now, are we dealing with that as part of the network? Or are we creating, if you want, a sub-network, which is just lunar? Because in this case, it may be life supporting, right? So the requirements are at a different level. I love the question though. I'm spending a lot of thought cycles on it and action cycles. So
I love that. It's when humans are on the moon, not if.
yeah.
So that's like get more.
Yeah, sure. So one of the questions here from Masood Bharati is about advanced power and energy supplies for the future of the spacecraft that you're going to be employing, and sort of what kind of challenges do you see, and what are your current sort of limitations on that?
Advanced power and advanced energy for spacecraft, challenges and limitations. Look, the best way of really amping up energy and power in space is for trajectories away from the sun, and is to bring nuclear to space. I do not know how to do that right now. There are so it's one of those, one of the games of innovation. You always want to ask how many miracles does it take for it to be successful. So this may be a 5 miracle type of problem, right? And probably 3 of them are on the regulatory side, and only 2 of them are on the science side. So I know science, not really all of it, but usually I trust science progress better than regulatory progress, just because it's hard to predict sometimes, because it occurs in a context of politics, and everybody who's an observer of politics realizes it's not exactly logical in all phases of the process. And so basically, so for me, I would argue that we're going to continue to focus on, advancing power solutions that are, of course, solar in nature. But the big breakthrough will have to be to really, if you want just cross the bridge into more nuclear. Now, understandably, that is a really complex thing. Suppose one of the countries that we think is not so friendly to the United States started putting nuclear reactors into space. That will get our attention too. So it's really important that we do it in a way that it's absolutely clear that this is for peaceful uses of space, and so I'm in no way want to belittle the regulatory and the political challenges that come with that. But that's what we need to do eventually to go forward, including if you want to actually have humans on the surface of the moon for longer than a lunar day, which must be a goal. The first expeditions will be 1 lunar day. What I mean with that is, to have the 2 weeks or so until it turns dark for 2 weeks, right? And it really takes a lot of energy. We do not know how to do the batteries to do that. It's really, it's colder on the moon than pretty much anywhere during the night, because there's no atmosphere.
So undergraduate student Todd Ackerman asked for an update on the Artemis launch system.
I think what he's asking about is the Space Launch System, which is it's going to launch the first Artemis missions, which is the largest rocket currently under construction. The update is that as of last week, we're starting stacking the rocket. So all the boosters have been tested, everything, all the subsystems have been done. And it's a huge picture. I mean, I want to go there to Kennedy, to the Cape Canaveral, and get up in that ginormous building. Remember that ginormous building with the US flag on it? That's where the space shuttle was stacked in it. So we're using that building to stack it, and it's using the whole building. A massive rocket that is coming together right now, still on track for a launch later this year. So this is going to be the best year for NASA ever if we stay on track with all of these, with Webb and the SLS going, both of them have kind of a complex history, shall we say. So that's what's happening there. I also think they overcame a lot of issues and are coalescing, building a really good team. And I couldn't be more proud of Kathy Lueders, my colleague in human exploration, who's really running this.
Is there a question here?
Yeah, I was wondering if you could comment about what is going to happen to the International Space Station in the future. We hear voices that the Russians want to leave, the Chinese are building their own. And the reason for asking is because there is such a beautiful research that is being conducted up there.
So let me talk about it. So first of all, the space station is good to go for another 8 years or so. That means we need to immediately start looking at the next solution. None of us in the US, irrespective of party, or anybody I've talked to wants a future in which we don't have presence in low Earth orbit that is enabling the kind of research you're just talking about. and also the training and the presence for explorers that are there. In fact, we're investing in even this year, investing in developing commercial type of capabilities of that type. We're gonna have to make a decision in the next 5 years or so, whether that brings us on track, whether we're together towards really achieving that without creating a gap, but that's what we're working on. We think that the future is one of partnership. Of course, International Space Station is one of the biggest demonstrations of international partnership, but I think the future is also one that also has the commercial partnerships as one of the key ingredients to its presence. We're focusing on it and are moving it forward.
I think we probably have time for one more question. And so let's see. I think from Prashant Krishnamurthy, sort of asking sort of what you see as the role and potential for quantum communication as something that NASA is interested in, and where you see it, that has a role for you.
I think quantum communication is a critical part of future communication infrastructure because of its safety and because of its robustness as we go forward. I think it's right now it's a really important research and analysis field. Multiple agencies are investing in it. We're trying to figure out where our spot is, where we can where we can have our imprint, kind of bring the best to bear that we have. And what we're doing right now is we're doing quantum experiments on the space station with a facility called Atom Lab. And part of that relates to the challenges that are there, namely developing entangled photons, and also develop quantum modems and underlying technologies. Most of the investments are happening in other parts of the agencies, but I just want to tell you, once I can buy it or I can really include it, I'll be first in line. As we're, of course, with the new incoming team, the new team in the White House, are trying to figure out whether there's a more specific role for NASA. Right now, the roles are really, as you know, in the Defense Department with DARPA, with frankly, Department of Energy, the National Science Foundation, as well as others.
Okay, well, we really appreciate your visit, and we promised we would keep you on time, and so let's give Dr. Zerlicka another hand. Hopefully we'll have you back again.
Yeah, let's do that.
All right.
Appreciate
Thanks,
it.
everybody.
Thanks.